Okay, let's switch to English. We're thinking about some correlation function. Okay, and we want to calculate this correlation function in the presence of the interacting theory. Okay? So to do that, we've seen techniques to expand that into some sort of power sequence. And then we can take into account all sorts of terms. The general idea is that there are terms that it's very easy to compute, exactly like the ones that we've discussed. And there are terms that are very difficult to compute. And as often happens in physics, you find that there are certain limits in which those that you can easily compute become exact. And that's typically, a combination of like a weak disorder, weak correlation, semi-classical limits, stuff like that. And it's not surprising, because you can see that if you do these approximations, you still have like quasi-particles. So effectively what happens to your theory is that it remains Gaussian. Okay, you remain with a Gaussian theory. But this is not always the case. Definitely not always the case. Yeah, in particular, in this specific problem, the kind of diagrams that we neglect are these diagrams. Now, what is happening here is that you can think about it as if a particle is scattering off one impurity. So the whole, because we're averaging over disorder, averaging over the locations of disorder, we're basically not allowing yeah, it's kind of like we're seeking processes in which you scatter to some momentum and then scatter back, which is what would be the intuition for that? Okay, there in certain cases, and I don't remember, there are some intuitive arguments to show, which I can't recollect right now, but maybe we can talk about it later, that actually this kind of diagram is small in 1 over KFL. Okay? Compared to the, for example, other higher order diagrams like this or this.
L, what's L?
What?
The mean free path?
The mean free path.
Okay. The what?
The mean free path.
Okay. Which is connected to the number of...
So VF tau is equal to that.
Okay.
So and typically the idea is that this process, it creates some like basically the electron scatters here, and then when it scatters back, it meets basically the exact same factor, and you assume that if in between it doesn't decohere, then it works. But this is some interference effect. So when phases matter, when the impurities are, for example, very close to each other, or the scattering is very strong, then you get this becomes important. But definitely we didn't take into account everything. Okay, so let's recall what we're doing. So we're talking about and what we discussed is we first started from real space. Real space RG. And the reason we did that is because it gives us intuition. It's much more intuitive, the real space RG. So I had a drawing that, you know, if you have a system that's divided into some sort of grid, okay, then effectively what we're thinking about is some sort of coarse graining. For example, we can take each 4 of these, then we go into a much coarser grid. This typical scale is delta x, and this typical scale is delta x prime, and delta x prime over delta x is what we call b. And then we basically repeat this again and again and again until something stops us. Either a coupling constant diverges, or we reach system size, or whatever. And in that way we can infer something about the theory, the relevant theory at low energy and long wavelengths. In particular, for the Ising model, at h much smaller than j, we found that the HDL is equal to h over j minus 1. And the JDL was equal to 0. That's what we found. And the nice thing about this is that this, although we're doing it far away from one side, it indicates the transition, the existence of a transition at h over j equal to 1. So that was one thing we did. Then we moved to Wilsonian energy. So the idea in Wilsonian energy is saying, you know, if we're coarse graining in real space, it's kind of like losing high frequency or high wave numbers in our theory, because these are responsible for these fine details. So he's saying basically, you know, if we're imagining, for example, a theory with some momenta k1 and k2, then the first and most important thing to define in RG is to have a cutoff. Okay. This is something, for example, in high energy they have a problem with, because they're talking about, you know, elementary particles. There are no cutoffs. It's everything. But in condensed matter and statistical mechanics, there's a very natural cutoff, which, for example, could be the you know, if we're talking about a spin system or a lattice or whatever, it's like the inter-site distance sets this cutoff. So this guy is lambda, and then the idea would be to you know, define a shell where this is lambda over b, and this b is associated in the same way with this b over here. And then what we want to do is we want to do basically 2 steps. The first step is to integrate out this shell, and then stretch the momentum, make a transformation to go back to the original theory. So we basically want, you know, S of j to have the same structure as some S prime of j prime. So the only thing that changes is the couplings. And if we're able to do that, we have a constructive way or logical way of defining this as a transformation, And Joseph was commenting about the relation between this and continuous Lie groups as a continuous transformation between theories. I don't, because I'm not an expert on anything, I can't really comment on that, but I know that these kind of definitions exist. From what I recall, there are issues with that. Like, it's not exactly a group in the full sense of the word, and there are some mathematicians are discussing this. But we're physicists, so we don't really care. So the way you do this kind of thing is that you define phi of k as what we called phi slow of k and phi fast of k. And phi fast of k is where k is actually bigger than this lambda over b and smaller than lambda. And this is where k is smaller than lambda over b. Okay? And then we saw that, for example, if we look at S0, which is 1/2 d dk over 2 pi to the d phi k squared plus r phi of minus k, then and here we assume that k is smaller than lambda, then we can actually divide this into two terms. One is the fast part, where k is in between this lambda over b and lambda. And this is what we call fast. And then we have the same thing for the slow. So let me call it just S0 slow. This would be S0 fast, for example. And then the idea would be to integrate out the fast mode. So if we have just a quadratic theory, for example, we integrate out the fast modes, it has no effect. And the only thing that really has an effect on this part is the stretching stage. The way we stretch So the stretching part is to define k prime is equal to bk, make a change of variables, and then basically S slow 0 becomes 1/2 an integral where this k prime is smaller than lambda, so it's like the same cutoff, we're maintaining the same cutoff, d dk prime over 2 pi cubed, but then we get, from this guy, we get a factor of 1 over b to the power of b, and then we have, inside here we have a k prime squared over b squared plus r. This is phi k prime, and this is phi of minus k. And now what we want to do is, okay, here there is a question, what do we define as a fixed point of our theory? And the idea is that typically what we want to consider, first of all, it's completely our choice. We can decide. But the most convenient one is to define this as our fixed point. And the way we do that is we define a transformation for these phi's. So we define a phi k prime of 1 over b to the power of d plus 2, okay, as equal to phi prime of k prime. And this defines a transformation for how the fields transform. Okay, and generally,
So it be d over 2, d plus 2 over 2.
yes.
Okay.
Sorry. So it's 1 over b to the power of 1 over 2 b plus 2. Is that true? No.
כאילו מה שכתבת קודם רק בשורש, כדי שזה יצא פעמיים.
Yeah, that's
כן.
what we have. Oh, that doesn't look right.
לא. והיה d פלוס 2 למעלה במונה.
Sorry. So what we want. Okay, let's denote this by.
d plus 2
Let's
over
denote
2.
this for a moment by
d plus
delta.
2 over 2. כן.
Okay. So what we want. So from this, we get that phi k prime is equal to b to the delta phi prime of k prime. So we want a phi of k prime prime. Phi of k squared to be equal to b to the 2 delta phi of k prime prime squared, and we want b to the 2 delta times 1 over b to the d plus 2 to be equal to 1. So from here we get that delta is equal to d plus 2 over 2. Right?
Right. כן, כן.
Okay. Now this is actually a Gaussian fixed point. But for a general fixed point, we would have that delta is equal to d plus 2 over 2 plus eta. Okay, that can happen. Okay, this is called anomalous dimension. Okay, this happens. Eta over 2. This is called an anomalous dimension, and it happens. In a Gaussian theory, we have eta equal to 0. Okay?
We're choosing to put the stiffness as the fixed point, right? This is the term
Yes.
for stiffness.
Yeah, we're choosing this is the common situation.
Yeah.
Okay, sure. Then what we find from this, okay, is that r prime after the transformation is equal to 1 over b to the d times, then we get this b to the d plus 2, right, times r. So this is b squared times r, we assume that B is equal to the e to the dl, where dl is something small, then we get our first RG equation, Wilsonian RG equation, which is this thing. Okay? And this just reflects the fact that if R is positive, then it flows to positive infinity. If R is negative, it flows to negative infinity. Okay? And in fact, a nice way of thinking about this equation is that we're thinking of R as a perturbation around our fixed point, this fixed point. So basically what we find is that R of L is equal to R of 0 e to the 2 times L. Okay, that's what we found. So it basically just grows and grows and grows. Right? Where did I write this? I don't know if I wrote it somewhere. Anyways, I remember. Okay, never mind. Probably yeah. What this means, what does it mean? It means that there is a certain point where this thing becomes order 1. Once it becomes order 1, it's no longer justified what we really mean is it becomes the order of the cutoff. I can describe this in a moment, but just let's assume, okay, that R of some certain scale, let me call it L star, okay, or LR, let's call it LR, is order 1. Okay. Well, that means that R of 0 times e to the 2L LR equals 1. Okay? And from this, we can infer that LR sorry, what did I want to say? Here's myself. Sorry. No, this is, sorry, no. Okay, let me explain this again. Okay. So, if we solve this equation, we get again that R to the L, sorry, R of L is equal to R of 0 e to the 2L, which is basically like R of 0 times B squared. Okay, now let's assume that this guy is of order 1. And now remember, what is this B? B is the size, okay, of these coarse-grained regions. Okay? So we're kind of growing. Now I'm thinking, okay, it's tricky because here when I said B, it was an infinitesimal. I can think of B as being some infinitesimal e to the dl, and then I can take B to, like, n would be the number of steps I make, and that would be like e to the n dl, which would be e to the l, like the scale that I've reached. So maybe we can just call this, I don't know, capital B. Okay, so this would be like this capital B. That's what we really mean. Okay, so it gives us the ratio between the large scale and the small scale. So what we find is that this B at which the divergence occurs goes like 1 over R0 to the 1/2. Okay? And this guy is basically like the large scale divided by the microscopic scale. That's what it is. Okay? So we get that our correlation length, let me allow to use that word, scales like A 1 over the distance from the quantum critical point to the 1/2. Okay? So this is another critical exponent known as mu. Okay? It means that the correlation length of the system, which tells us about, you know, the typical size over which, you know, you see kind of the critical behavior. It means that when you're smaller than this size, the system looks critical, and it's still controlled by your fixed point. But once you reach this thing, one of the couplings diverged and stopped the flow. This coupling is important because it's the one that controls the phase transition. For example, you could think of R as, you know, as a tuning parameter of an Ising theory. We'll get to that in a moment. So, and this is exactly the kind of exponent you expect to get from Ginzburg-Landau theory. This is like, if you like, people like to call this a mean field theory. So this is the mean field theory exponent, or the Ginzburg-Landau exponent. It tells you that the Gaussian theory, as long as you're controlled by the Gaussian theory, you get these kind of very simple exponents that you could get from a Ginzburg-Landau analysis. Now, the next step is to take into account interactions. Let's see if I have anything else.
What is this zeta overlay?
So again, what we're doing, okay, is you'll see later how this is related, but basically we're coarse graining and coarse graining and coarse graining. Okay, and as long as this R that is flowing now, as long as it is a small parameter, like a perturbation, we can still argue that what we have here is a system that's controlled by the critical theory. So it looks critical. Okay? But then there is a certain regime where you become so large that you suddenly begin to see that you're not controlled by this critical theory. That there's a mass, there's a gap. A good way, okay, let me try and give you what would be a good intuitive picture. Let's think of let me see if I have a good explanation using thermal fluctuations. So if you have thermal fluctuations, yeah, okay. I think the best way to think about it is this: is if you look at this Green's function, this Green's function you see, this Green's function, if you only consider this part, it has algebraic. It leads to algebraic correlation. So, for example, in 3 dimensions, it decays like 1 over r squared. We also saw that. In fact, we concluded last time that g of x, if g of x, which is phi of x, phi of 0 is some correlation. Using this transformation, it's basically like b to the minus d minus 2 g prime of x prime. So, and the reason for this is because this guy, okay, is the Fourier transform d3k over 2 pi, d dk of 1 over k squared e to the I kx. Okay, so the fact that this thing goes like k squared makes it, gives it the structure that it is up to a rescaling, it looks the same.
Shouldn't it be plus r, k squared plus r?
What?
Shouldn't it be k squared plus r and the denominator?
No. Okay, that's exactly the point. Exactly the point. So the question: if r is small, okay, then there's only a very large scale where this r becomes important.
Okay.
Right? Because only a very small k becomes important. So if most of the k's of your theory, like the cutoff, is much larger, okay, then when you look at these small scales, okay, it's controlled by this kind of behavior. You need to go to a very large size to feel that the influence of R. Okay, that's exactly what this RG is telling you. Like, these are 2 different viewpoints on the exact same thing. So you can look at the Fourier transform, okay, and in the Fourier transform language, like you said, eventually, so what happens is that because you have this R, then at long distances it will decay exponentially instead of algebraic. And the fact that it decays exponentially means that you have some typical length scale in the system. And that length scale is what I call psi. This is this correlation. So, it means that if R is equal to 0, then your theory actually is the correlations tell you something about how configurations of the field would look like. And the point is that they're fractal. They're like scale invariant. Because at any scale, they look exactly the same up to some factor which you can absorb. So there is no typical scale that you can assign, length scale that you can assign for this Green's function. Okay, so that's basically the point. And this psi here is exactly the length scale where this breaks down.
Okay.
And and this appears in any, like, I don't know if you've studied the Ising model or whatever, and you discussed correlations, probably studied in statistical mechanics something. You never talked about critical exponents?
No, we talked about it. Yeah.
But you don't remember?
It was a few years ago.
Yeah.
So, near criticality, any small fluctuation will impact the system as a whole, right? That's what this means.
Well, the fact that the correlations decay algebraically means that it also means that a perturbation has an effect that decays algebraically into the system. Yeah. That's also true.
And the A is like the difference between the atoms.
Yeah, that's the initial skip. So the point, this thing tells you that at each step of course graining, we're increasing the length scale. We're starting from the microscopic scale, and then doing another one, another one, another one, another one. And then the meaning of solving this RG equation like this would be, performing all the coarse graining from the small scale all the way up to this psi scale where, criticality breaks down.
Okay. And why is it when R is equal to 1 like that?
Because from the viewpoint of RG, it's just like saying that your RG is no longer valid because your coupling constant is not a perturbation anymore. Okay. But there's another way to view this. You could imagine. Let's really look at our dispersion. So if I draw the dispersion as a function of k, and let's assume that initially r is very small, it's like here, and then our cutoff is like this is like minus lambda, and this is lambda. Then our theory is kind of linear, and it curves down here. Okay.
Okay.
Now let's imagine that I have a small, here this is lambda over b and minus lambda over b. And I integrate over this window. Okay. And now I want to re-stretch. Okay. So I'm left, after I integrate it out, I'm left with this dispersion. But I want to stretch it. So when I do that stretching, you can imagine that it's like stretching this to here, stretching that to there. So we'll have something like this. And as we stretch more and more and more, eventually this guy will start to increase. It start to increase, but it increases until it reaches, this cutoff. So for us, in our case, there is no difference between dispersion, like we put all of the dimensions together, but yeah. But this is the kind of physics, and then you stop when this R reaches the magnitude of the cutoff, and that's exactly what we describe here.
Okay. I can ask some more questions, but I'm
You
not
can
sure.
ask.
Yeah, it's fine.
Yeah.
But like our I understood that when R is equal to 1, so if you do a perturbation theory series in R, then obviously it's not valid anymore, I guess. But I'm not sure how it's connected to like this point in the middle when
Good.
k is equal to 0. This is the height of it is R, right?
Yes.
But it's so R goes to 1, not to.
Oh, good. So so that depends on how you write your units.
Okay.
So this equation is invariant under a rescaling of
Yes.
R. But when we say that R reaches order 1, so that's just a statement. Typically what we do is we rescale our, you're right, I didn't explain that properly. Typically we rescale our couplings such that they are dimensionless. And when they're dimensionless, you stop when they're order 1. When they're not dimensionless, and here R does have dimensions, then you need to state what you mean. So actually, we shouldn't have written here 1. Where is the here. What we should have written here is lambda squared. And this lambda squared is exactly 1 over a squared. So that's where this a comes from.
Yes.
Okay?
Yeah. Okay.
and that makes sense, because once it reaches this limit, then this but again, you have to understand that when you're doing RG, it's all kind of very back of the envelope-ish, or this is not an exact calculation. This is kind of a scaling argument, like how does this length scale with the distance from the quantum critical point? And if you look at this thing, it's completely trivial, because you see that this guy, if this has units of whatever units it has, this has to have some units of length, and they scale with length like the square root, because this is squared. It's completely trivial. It's a property of a Gaussian theory. Okay? And as long as the theory is indeed controlled by the Gaussian fixed point, you're going to have these kind of critical exponents. Like this eta here is going to be 0. This nu is going to be 1/2. There are other exponents like beta, which you might also know is also 1/2. That's how the order parameter goes to 0. And so on and so forth.
All the Greek letters you want.
Critical exponents. Yeah. Okay, so now let's take into account interactions as we...
Yeah, we did the calculation.
What?
We did the calculation.
Yeah, we did it last time. So the idea... Yeah, this is all just a reminder. Maybe I'm wasting too much time. I won't be able to get the fermions. So now we take into account S4, which is U over 4 dr phi to the 4th, which is equal to U to the 4, pi phi 1, phi 2, phi 3, phi 4, delta D, sum over K. Okay? And then we saw that naturally this guy divides into 4SS plus S4SF plus S4FF. And then our claim was that what we want to do is integrate out these fast modes. And we wrote, and therefore, after integrating out the fast modes, we get that SS prime becomes S0S. Okay, I haven't stretched yet. Okay, I didn't stretch yet. I'll stretch in a moment. S interaction SS minus ln of the expectation value of e to the minus Si SF 0. And this is average using Gaussian fast theory. Now, because it's Gaussian, we said that the expectation value of e to the minus SISF is equal to e to the c, where this c is equal to minus ISF plus 1/2 S ISF squared minus SISF squared plus other terms. And we're only going to focus on the first two terms now. So, for example, we saw first term is basically, this is one order of the interaction. So the only way we can contract it is if this is fast and these guys are slow. And then this guy becomes 3 times SD minus 1, which is the area of the sphere in d dimensions, over 2 pi to the d, an integral from lambda over b to lambda dq q to the d minus 1 q squared plus r. And we saw that if b, I remind you that b is equal to e to the dl, very, very small, then this becomes 3 times s to the d minus 1 divided by 2 pi to the d lambda to the d divided by lambda squared plus r dl. So that's one thing we did. And then this guy, let me call it delta SF I squared. So this delta SSF I squared, this was basically equivalent to this diagram. Now, why only this diagram? Again, this is fast because we're integrating over it. This is fast, but the outgoing legs are slow. And why do we have only this diagram and, for example, not this squared?
Because of the squared there.
Exactly, because of this. So this guy is exactly just this guy squared. But then this guy we can contract in different ways, as we've learned when we've studied Feynman diagrams. But the one where we contract them internally cancels out with this. So we're only left. So this cumulant structure basically tells us that the only corrections that come in are these fully connected diagrams.
So this is how RG works with disconnected diagrams, deals with disconnected diagrams. In general, in perturbation theory, we have vacuum fluctuations, and the partition function annihilates those. And
right
here is this,
yes,
the one that,
right,
this mechanism.
Mm-hmm. Somehow, magically, they always disappear. But you do have to, there are two different things. There are vacuum fluctuations is one thing. That's basically, contracting completely internally. That's not what we're talking about here. Here it's still connecting, but we can we can just choose the fast modes in such a way that we get a contraction like this.
Okay.
And that cancels out. And this thing we saw is equal to 9 SD minus 1 divided by 2 pi to the d lambda to the d divided by lambda squared plus r squared u squared now dl. Now the point is that you see that these contributions, they come with opposite signs, and that's important because this minus sign means that when I add this guy here, he actually adds up positively to this S term. But this guy who comes with a plus sign, with a minus sign, actually adds up with a negative sign. Okay?
By the way, there's something interesting about when you calculate this correlation function is that you had a diagram that have two inserted particles and two outgoing, but you also had a diagram with 1 and 1, right?
Okay.
So it's
This, you mean this one and this one?
yeah, it will that they contribute to the same correlation.
Why do you say that they contribute the same correlation?
I think the second one you said it's this without with the first one twice.
So this term here,
Yes.
if you write it down,
Yes. Yes.
okay, sorry, if you write this term down,
Yes.
okay? I kind of skipped a lot of stuff because we already did it when we studied RG. But this guy is actually writing the interaction term twice, this term,
Yes.
and then deciding how to contract it within a Gaussian theory.
Yes.
Okay, it's kind of like the story with perturbation theory. This is taken with a 0. So when we do that, all I'm saying is that, you know, how you decide to take the, you know, it's a Wick theorem.
Yeah.
So you know, you don't. So if I write phi 1, phi 2, phi 3, phi 4, phi 5, phi 6, phi 7, phi 8, okay? And this is like coming from one vertex, and this is coming from the other vertex.
Yeah.
Then I don't have to connect them like this. Right? I can also connect them internally. You know, say I chose that 3 and 4 and 5 and 6 are fast. Then you also have the combinatorics of choosing, you know, how to choose them, and this leads to this factor of 9. But I'm not getting into that. But let's say I chose that this is slow and this is fast, in such a way that I'm contracting over these guys. Then I actually have, I can also contract them in this way. It's allowed. But if you do that, you'll find that it's exactly like this term, just squared. And that's exactly what's written here.
Yeah.
So they cancel.
Yeah.
Okay. So now we can write our G equations. Which I think is where we ended the last class, right? So we have the R to the L is equal to 2R let me write, okay, for now let me write it like this. Later on I'll correct it. 3SD minus 1 to the D, lambda to the D, lambda squared plus R, and moment. This is U, and the U, the L is equal to 4 minus D. Oh, this I forgot to mention, but okay, let me just quickly remind you also this. So when we rescale these guys, okay, then this guy gives us a factor of B to the D. These guys give me B to the D plus 2 over 2 to the 4. And then these guys give me 1 over b to the 4d. Okay? So if we sum all of these up, you find that the whole thing together, okay, this whole thing goes like b to the d minus 4. Right?
Right.
Okay? So this is this 4 minus d that you see. Okay? So this is what we call the tree level scale. And then the next term is now negative because of this issue of the signs I've just told you. We have 9 sd minus 1 divided by 2 pi to the d, lambda to the d divided by lambda squared plus r squared times u squared. And now let's see what these RG equations really give us around the Gaussian fixed point. So first of all, we find that the Gaussian fixed point is still a fixed point. So we can make an expansion. I did it last time, but let's not waste too much time on it. Using that expansion, we can basically find that if d is larger than 4, then we have our separatrix here. Okay? And the flow around this separatrix is basically like that. Okay? What it means is that if you, and this is u, by the way, and this is r. What it means is that if you start anywhere above the separatrix, you flow to positive r, which is one phase. Okay? And if you're below the separatrix, you flow to negative r, which is the other phase. Why do I say that? Because remember that we have a connection to a Ginzburg-Landau theory, right? We can write a Ginzburg-Landau theory, which is something like, r phi squared plus u over, r over 2 u over 4 phi to the 4. So, we have some average phi within Ginzburg-Landau theory, or maybe we can write phi min is equal to the square root of minus r over u. So that implies that, if r goes to negative values, you have, like, this is ordered, this is like disordered. Okay, and this gives us, you start, you place yourself where you have your microscopic values, and then they flow away. And if they flow to positive r, you're going to the ordered state, and if not, to the other one.
What do you mean by disorder and order?
So this is this connection to the Ginzburg-Landau theory. I'll get to that later on more, but the phi to the 4th field theory is essentially, for real fields, it's basically the Ising transition. Okay? Because you have like 2 minima, and they're equivalent.
And it seemed like that when you flow up, you don't have a minimum, right? Because this is imaginary.
Yes, exactly. So that's when r is positive, it's like the disordered phase.
So
where phi min doesn't have
is zero.
Is zero.
And how it's connected to order of what?
So I don't know what this describes. It's a generic thing.
Yes.
But let's assume it's like Ising models, or it's like spins.
Okay.
So it means that the average spin is 0.
Okay. So
Okay. And here we have something else. Here it looks kind of like So it basically looks like this. This is U. And this is for the smaller than. So what we find is that when so here we have a description that we can very easily associate with the phase transition. Okay, so there's a separatrix. It separates between the ordered state and the disordered state, where you have one direction in which the fixed point. This is like the fixed point, and there's one direction in which the fixed point is stable, and another direction that tunes the instability. So the critical theory will be controlled by this separatrix, and all the correlations, for example, all the properties of the theory will be controlled by the fixed. Here we don't have that. We're lost.
Right, but you still can draw a line which on the upper side you have positive R and positive U, so
no. But the problem is that what we're looking in order to describe like a critical theory. So the point is, let's say I'm very, very close to the separatrix.
Okay.
Then I can say something about, like, I can flow along the line.
Okay.
See, until R diverges, and then I stop, and I can say, like, I reach very, very large scales, and I can say something about critical properties, about correlations, about these critical exponents. I'll talk about that in the end.
Okay.
And they're going to be controlled by the behavior around this fixed.
Mm-hmm.
That's what's going to control them. Here we can't do that. So what's going to happen is that if you start here, you're going to float a like huge U. Okay, you can stop, but it won't be useful in any way. Like, you won't be able to, you have a extremely strongly interacting theory. You can't say anything.
Still, a phi minimum is a finite amount, finite positive amount.
I don't know. It's like anything can happen because it's a theory that we can't solve. So what would be a good way to explain this? Yeah, that's a good point. So why? What you want to say is that there is some sort of, okay, maybe I would argue this. That it's not exactly true what you're saying, because you see these points here. If you allow yourself to reach very large U, then maybe you can draw a line here where everything above it goes in one direction and everything below goes in the other direction. But I would actually argue that there's going to be a whole intermediate region where U becomes too large before R becomes too large. And then I don't know what to say about that region. Of course, you're right that if I'm very, very close here and I just flow there, or I just flow here, when I'm far away enough from this critical point to begin with, then you're right. Then it's it's clearly, if you tune R to be very large or very small, you're going to go from like order to disorder. But if you want to say something about the universal properties close to the critical point, this doesn't help you in any way. Like, you can't say anything intelligent.
Okay, I think I need to understand what you mean by universal properties.
Okay, so maybe a good example, the best example, the most important critical exponent, most commonly used, is nu, the one we just talked about. So I want to know something about, and nu is the easiest one. It's the most direct one, because what you do is you rescale and rescale and rescale until, R cuts you off. For the reason we just explained.
Yes.
Okay? there's going to be an intermediate regime in this phase diagram. So, maybe here, you're right, you have like one thing, and here you have another, but in between, you're going to have a whole region where U explodes before R. U cuts you off instead of R cuts you off.
Okay.
And that scale I can't associate with correlation length anymore. Because that's a different behavior. That means that my theory becomes strongly interacting before it becomes massive. Because that's what we're really describing here. We're describing the point where the theory becomes massive with some typical mass.
Okay. Okay. But still, if we return to this simple equation,
Yes.
you have this solution. So if U explodes more than R, so you have the zero solution. So it's a disordered system.
Yeah, but again, what? Okay. No, that's actually not what happens.
Okay.
There is. Okay, what I will argue is. Okay, we'll talk about it in a moment. Is that there still is a phase transition? Okay, the transition is maybe like a way of interpreting what you're saying is like a first order transition, which can happen, but it turns out that there still is a continuous transition. Okay. For example, in 2D, we know we have the Onsager solution. It's a continuous transition, for example. The flow would still look like this for 2D. So that's not true. So there is a yeah, I don't know okay, let me put it this way. You're not being completely fair with me, because if I would just tell you, okay, let's just associate the explosion of U with a disordered phase, then your immediate question would be why? And then I wouldn't have any reasonable argument for that.
Okay.
Because the argument I just made about the fact that as long as U and R are small, it means that the critical theory is controlling everything. But if the first thing that explodes is U and not R, then I can't associate that explosion with, a correlation. It's something else that is happening.
Okay.
And the fact is that then our theory becomes strongly interacting. Fluctuations become important. And I don't have a way to deal with it.
Yes.
Okay? But that's exactly what I'm getting to now. So maybe this was like a reminder of what we had last time. So let's take a break. And after the break, we'll see how Wilson and Fisher approach this problem.
And also the interesting thing happens between 2 and 3, right? Dimensions. Because
Why?
above 4, we can easily do mean field.
Yeah, what you're saying is that 3 is the interesting dimension.
Yeah, exactly.
In fact, that's exactly the point. So the point is that what I'm going to argue later on is that, example, the liquid-gas transition can be considered, and any kind of critical point where you have like a first-order transition terminating is generically this Eisen universality. So it's very general, and yes, they happen a lot in 3 dimensions. So that's the actual dimension that we're interested in, and it's something we cannot solve. So we don't have Onsager's solution for 3D, and on the other hand, RG seems to fail, and that's where Wilson and Fisher comes in. Okay, so that's what we're going to see, how they actually approach this three-dimensionally. So yeah. So maybe we come back at 4:30.
נזרוק את הפלאפל עכשיו בסוף ההרצאה? כן, לא...
אה,
כי כאילו יום חמישי, אם הוא לא
כן.
נאכל עד סוף ההרצאה נראה לי...
כן, נכון.
אז
וגם אין סטודנטים.
כן.
אין
אבל לא.
אין אף אחד.
טוב.
ואני לוקח את זה לרעננה,
תיקח, למה?
למרכז קליטה. חדשים.
כן, כן, תיקח.
נהיה שמחים.
אני בטוח. טוב, נראה ששברנו את הארגז.
אתה מדבר על הפלאפל?
כן, כי אמרתי ליוסף שאולי נזרוק אותו אחרי ההרצאה, כי אף אחד לא יאכל אותו אם עד עכשיו הוא לא נאכל. כאן יסריח כדי להישאר שם, אבל אם יש לך למי לתת אז זה עדיף כזה.
כן.
באתי מוקדם מדי?
לא, צבי רגע נראה לי הלך לשירותים.
Okay. So when we talked about the Dirac theory, we mentioned that in one stroke of genius changed physics. Well, this is of course not to the same extent, but Wilson and Fisher, in this brilliant idea, did change physics, maybe not to the same extent, but pretty serious. So what they decided to do, they said, okay, we have a problem because the dimension is something discrete. So for 4 and above, everything looks good. For 1, 2, and 3, everything goes completely wrong. But what would happen if we would try to think of the dimension as a continuous variable? So they say, let's write d is equal to 4 minus epsilon, and epsilon is much, much smaller than 1. Okay? Then we can expand these RG equations in a controllable way. So the above equations become 2r plus au minus bur, and du dr becomes epsilon u minus 3bu squared, where a is defined to 3 times s to the d minus 1 divided by 2 pi to the d times lambda squared. And we can absorb this lambda squared into the definition of r like we did before. And b is equal to 3a divided by lambda squared. So b is dimensionless because a has units of lambda squared. So u is a dimensionless coupling constant close to 4, and r we can make it into a dimensionless coupling constant. Okay, very easily. Now, when we did this expansion, you might ask yourself, what did we actually expand? So here, this is obviously, minus epsilon. Sorry, epsilon. This is obviously epsilon. But here, when we make the expansion, then you need to ask yourself, what is the typical scale of u? And we will see that u scales as epsilon. So if we're making an expansion, then this thing actually already scales like epsilon squared. And to be consistent, we need to expand everything else up to order epsilon squared. So when we do that, it turns out that these guys, this dependence on D can be neglected and just taken to be 4. And now if we look at these equations, the situation is different. So the Gaussian fixed point is still a fixed point, but it's an unstable fixed point. But then we have a stable fixed point, which is the Wilson-Fisher fixed point. So a second fixed point emerges. And this is U. So it's easiest to start from this equation. So how do you find a fixed point? Oh, it's not the R. You just equate this to 0. And then you can see very easily that this guy is epsilon over 3b. So as promised, this is order epsilon. And RWF is minus a UWF divided by 2. So we just plug this in here. So we put UWF over there, UWF here.
You also did an expansion here that's not related to our continuous dimension, right?
Yeah, you mean that. Okay.
You assume the R is smaller than
Okay, so the point is, previously, I didn't, because U at the fixed point was really 0,
Okay.
then I didn't need this correction here. But once this correction becomes relevant, I need to ask myself, up to what order am I expanding? And because here I have order U, and this is order U squared. So we're going to see that U and R at this fixed point are at the same order. So we're going to show you in a moment. So if we expand this to U squared order, we need to also expand this to, like, there's R, there's U, and there's also U times R. So I need to expand in R.
So you
But here I don't need to do that because it's already U squared.
But you also assume that R is smaller than gamma squared.
Lambda.
Lambda squared.
Of course, because that's exactly the point where it cuts off the flow and I no longer need to. Right?
Yes.
That's what we were discussing
when it,
before.
Yes, when it does not behave this way.
No. When R reaches the scale of lambda squared,
Yeah.
that scale is exactly psi. That's what we discussed before.
Yeah, but when it does not, but you assume it does not.
It has no meaning to assume that it does, because if I do, it means that I'm already in the ordered or disordered state, far away from the critical point,
Yes.
and I don't care about this.
Yes, okay.
So I'm exactly, what I exactly want to be is close enough to the critical point to see the critical scaling. And this is something I can, it's not just doing that, because people can measure stuff. So for example, we'll talk about this in a moment, but you can so you can do experiments where you really measure these kind of things.
Yes,
Okay, we'll talk about this in a moment, but you can, in a liquid-gas transition, okay, maybe I'll talk about it now. If you have a liquid-gas transition, and it ends at a critical point, so this is pressure and this is temperature, then, and this is like liquid, this is gas, okay? So, on this side, you know, your liquid minimum is lower than your gas minimum. And on this side, it's the other way around.
Yes.
Okay? Yeah. And that means that on this line here, they're actually equal. That's what defines this line.
Yes. Yeah.
So if you move along this line here, and here, what happens at this point, you have just a single minimum. And as you go from this to this, it's basically, this thing is smooshing into that, and then this reemerges.
Okay, nice.
Okay? And at this point here, it's really like that. So what it's telling you is that if you move along this line, it's really like an Ising theory. So, for example, you can do an experiment where if you measure this trajectory, this contour very carefully, then you can perform experiments. So you can, for example, you can take, you can measure correlations, for example, between gas and liquid in the system along this line. And initially you're going to see fluctuations, and they're going to decay, like some power law, until they reach a typical scale. Well, one of them will take over, either the liquid or the gas. And you can do that, and you can measure very carefully these exponents, and you can see them, and you see that they deviate from, mean field theory. So nu, for example, is not time in this measurement. So why did I say this? Why did I say this? What was your question?
I asked about it. I guess expanded in R.
I don't remember. But
I said that you read the expansion in R smaller than.
Oh, I know what I wanted to say. What I wanted to say is that, okay, then the universal behavior is close to this critical point. So if you're far away, if you're here, okay, and you're deep in your ordered state, then you start to look at larger and larger distances. It's very, very quickly like these inclusions, these bubbles of water in a otherwise gaseous system. They're very small. You have very small droplets. As you move towards this point, let's say you initially you deliberately start from an initial condition where you have gas. But as you grow to this, you move along this line, you're going to have larger and larger droplets. Okay?
What do you mean by droplets?
Droplets of water. Droplets of water.
Yes, I'm not sure how it's connected. But okay, but
what do you mean? This is liquid. This is gas.
Yes, but you're saying you started with gas, and you're on this line between this gas and liquid. And although you started with although you're on this line, you're having more and more liquid, right? That's what.
Yeah, because you have more. What's happening? Okay, so what's happening is that you have a system. This is gas. This is liquid.
Yes.
Okay, and you're starting deliberately from this side.
Okay, and you're lowering.
But now you're moving along this line, so these are becoming more and more shallow. So fluctuations become stronger, and you see these liquid bubbles.
Okay.
So these liquid bubbles, you see, they have a typical scale to them.
Okay. Yeah.
This scale is Xi.
Okay. Nice.
Okay. And as you come closer to the critical point, they're gonna grow.
Yes.
Okay. And their shape is actually fractal. It means that when you look at them at the scale smaller than Xi, you see all sorts of bubbles in bubbles and structures and stuff, like as if you don't know, as if there is no scale. Because the correlation, if you look at correlations inside, smaller than this bubble, it's actually not a bubble like that. It's more like a complicated structure. But if you look at correlations that are small compared to the bubble size, its typical scale size, then you can't tell if you're in this phase or that phase. Okay? But when you reach a large enough size, you suddenly understand that you're gas. Okay? But as you come closer, this length scale becomes larger and larger and larger. So what does that mean? It means that when R is large, the physics is kind of boring. What you're going to find is that
when R is large, we are up around this curve, right?
the Ginzburg-Landau theory is going to be very good because these are going to be very deep, and the fluctuations are going to be very small around this minimum, and the expectation value is going to be just for example, phi expectation value, if you can assign something like that, to do that, you need to do some analysis because it's not like measuring, magnetization. Mm-hmm. You need to make a picture, and you need to say everywhere I see water, it's like up. Everywhere I see gas, it's down, and then you kind of measure an order parameter. If you do that, it's going to be this minus R over U, whatever is the parameter. So it's going to be very simple. And if you measure, how this psi changes as you go along this line, it's going to be completely controlled by the mean field exponent 1/2. But as you come closer to this critical point here at the end, something is going to start to deviate. And that only happens very close to the critical point. And that's the whole point of this analysis. The whole point of this analysis is to say that we're going to be very, very close to the critical point. And what you're talking about, this thing, that's like very, very far away. Okay? So, but the whole point of this coarse graining business is that we're lowering the cutoff. Okay, so initially, if from the very starting point, this and this are of the same order, go away. You don't need RG. We don't need to talk. We're talking about the situation where R is very, very small, and we're looking at how it coarse grains, and we want to see how it reaches this eventual running scale.
Why don't we need RG?
Because we've already if these are of the same scale when you just started, that's like saying that these droplets of water, their typical size, is already at the microscopic cutoff, which would be, I don't know what. So maybe in your experiment you have some cutoff, or the interparticle distance. It's basically like being deep in either, like when you're very deep here, it's very sharp. It's either you're gas or liquid. It's true that if you're a little bit above, you're going to be exactly liquid, and you're a little bit below, it's going to be exactly gas. But on the line, it's going to choose this or that in a very sharp manner, which is what Ginzburg-Landau theory tells you. It's like symmetry break. It's this or that.
Yeah.
If you're very deep, if these are very deep, it's like all spins are up or all spins are down. It's very hard to find, fluctuations, bubbles, where inside the up system you suddenly have a bubble of down. That only happens when you come closer and closer to the critical point. And that's what we're talking about. So when you're far away, these fluctuations, they're going to look like mean field fluctuations. Nothing interesting. Okay? But we definitely want R to be much, much smaller than the initial cutoff. Otherwise, there's no need to use RG. You can just use Ginzburg-Landau. You know what you're going to get. That's what I mean. Okay? So now let's go back to our thingy. So, sorry. We plug in this result here. Everything becomes proportional to A. Okay, and we get that this thing is minus A epsilon over 6B.
Basically, from a mathematical point of view, what you're trying to do now is singular perturbation theory.
Yes.
Okay.
Oh, that's, you're taking it one step ahead. What you're saying is that I'm going to get the first couple of steps as a function of epsilon,
Mm-hmm.
and then if I cleverly resum it, I can take epsilon to 1, assuming I have some analytic form, and then I'm going to get the results for, yeah. But that's, first of all, we're not going to do that.
Okay.
But that's, years of study following Wilson-Fisher development. People found, ways to improve and improve. Like the stupidest thing you can do is just take epsilon to 1,
Yes.
using this, and then get some critical exponents. And that gives you an okay result. But then, as you know, scientists are very, looking for stuff to do. And anybody who does these kind of, Padé approximations and all sorts of techniques to resum it better, take higher order diagrams and, do higher order x in epsilon and stuff like that. People work, and indeed, but the amazing thing is that they were capable of getting the exponents. So the agreement with experiment is amazing. Okay, so basically, now we can expand to linear order around the new fixed point. We get the following equations. We get d to dl of delta r delta u. So delta r and delta u, delta r is like r minus r Wilson-Fisher, okay? And this thing is equal to 2 minus b Wilson-Fisher, a minus b r Wilson-Fisher, epsilon minus 6 b u Wilson-Fisher, 0, delta r, delta u. So lo and behold, we have restored peace in the universe, because now we have two eigenvalues for this matrix. One of them is 2 minus epsilon over 3. And lambda 2, this is like, let's call this lambda r. And this lambda u. And this guy is minus epsilon, meaning that it is a stable fixed. So let me make a drawing. What?
No, okay, no.
Let me make a plot. So we have r. We have u. Then we have our Gaussian fixed point. And then we have here our Wilson-Fisher fixed point. So this here is u Wilson-Fisher, and this here is r Wilson-Fisher. And we have, so along this line we have stability. Okay, and anywhere away from this line, we see flow like this. Sorry, this is not true. So if I'm very close, I flow like this. So this is the unstable direction. This is how it looks like. So this, what is this?
The separate.
Yes, this is our separatrons. It means that if I start below, I flow to the ordered side. If I'm above, I flow to the disordered side. But I'm now controlled by a different fixed point. That's the point. For example,
what's lambda? The exponent.
what is lambda? Lambda is, it's the eigenvalues of this matrix. So for example, if I compute d delta r over dl, I get delta r of 0. It's lambda r delta r tilde, and from here I get that delta r tilde around this fixed point here. Actually, it's the same r, so I don't need to call it delta. In this case, that's very convenient. So I get that delta r of L is equal to delta r of 0 times e to the minus this lambda r L. And what that implies is that our critical exponent now is 1 over lambda r. Instead of 1/2, we get, for example, what do we get? We get 1/2 plus epsilon over 12. So according to this, in d equal to 3, what do we get? We get 1/2 plus 1 over 12, right? Because if we want to reach 3 dimensions, epsilon is 1. So this guy gives me 7 over 12. What is 7 over 12? Maybe you guys can tell me.
Nothing.
I have to check. What?
You can't.
More than 0.
No, but what does it give? 0.5
something.
Yeah.
0.
Maybe 0.6.
Because 1 over 12 is it's my
Yeah.
So it's 5 what?
7.
So this, the real critical exponent measured, for example, in numerics or in experiment, is, where did I write this? Here it is. It's new experiment. Is 0.63. So it's we have an error, but it turns out that what Oz was mentioning before, by using clever resummations, they're capable of getting this exact exponent. So if you do it more carefully, you expand higher orders in epsilon, and you do some resummations. So the idea would be that nu, see that you think about nu of epsilon as some nu of 0 plus epsilon nu tag. Right, let's call it here 1, tag of 0, and you try to resum it. And here we have obtained like the first order, but they do better. Okay. And the whole liquid gas phase diagram I explained to you. Maybe I can also comment about. So in my notes I explain about other critical exponents, but I think nu is the most important, simplest, and easiest to understand critical exponent. And I think it exemplifies the idea. So the idea is that they understood that basically what's happening is that when you jump from 3 to 4, it's like, you know, you jump from like this fixed point is just, you know, jumps to, you know, very, very high values, and you're in trouble. But if you expand in a small epsilon, then you still have these values occurring at controllable at points where your theory is still controlled. And you can use this epsilon to control the calculation. And this result is really, really important. Let's start from the fact that it's one of the, if not the most important paper. It's one of the crucial papers that awarded Kenneth Wilson the Nobel Prize for RG. It's also one of the most successful demonstrations of the RG procedure. Okay? And it's also a tool. So now many people use this idea to calculate all sorts of stuff. So it's and if you think about it, it's really an astonishing result, because think about the fact that, you know, the whole point of the breakdown of mean field theory is telling you that, you know, these quadratic, this quartic term becomes important. Fluctuations are important, and it's very, very difficult to take them into account. And what Wilson and Fisher show is that they have a very elegant way, very simple, okay, to take into account the effect of fluctuations in a meaningful and useful way. So it's really a groundbreaking result. Okay, so with that, we're done with RG for the fight of the fourth field theory, and now we start. Probably the last topic we're going to cover is RG for fermions. So before I do that, do you have any questions?
This is nice. It's very, very nice.
Yes.
It's like a maggot in an apple.
Like a maggot in an apple?
Yeah, like כאילו מה יותר גרוע מלמצוא תולעת בתפוח? למצוא חצי תולעת בתפוח.
Okay.
מה יותר גרוע מחצי תולעת בתפוח?
Yes.
It's like 1/4 maggot in an apple. What was? שמינית, וכן הלאה וכן הלאה. מה הכי טוב? לא למצוא תולעת בתפוח. כאילו מקבלים שתי התנהגויות שונות לגמרי, כשאפסילון שווה 0 וכשהוא הולך ל-0. זה לא אותו דבר.
מה אכפת? כאילו נראה לי חצי תולעת זה גם...
The way, אוקיי, מה אני מכיר את זה בתור בדיחת שואה. שמה יותר גרוע מלמצוא חצי תולעת בתפוח? השואה.
לא.
I know all sorts of versions of that joke, which I cannot tell. I might be fired if I tell you. Yeah. I should invite the Mossad to interfere with the obviously show that they can. Yeah. Okay. So
now you understand why she taught mathematics.
It can actually be important for something. But the point is that, like, the people who actually do these resummations to actually get the result, they really should be admired. That's like really fun. Okay, so fermions.
Yeah.
So
Why do you call it resummation? What do you mean by this?
So the philosophy behind this perturbation theory. So first of all, why do I call this a groundbreaking result? Because the most straightforward thing to do is to think about our couplings as small and try to do perturbation theory in our couplings.
Yeah.
They thought outside the box and did the same kind of perturbative approach, but in the dimension.
Yes.
Okay? And when you do perturbation theory, we already talked about this. So if I look at my, we talked, in the beginning of this class, we talked about the Green's function.
Yes.
Okay? So let's say I have my interacting Green's function. Again, I'm thinking about it as a function of some coupling lambda.
Yes.
Then, I don't know how to compute that. That's difficult because the theory with lambda is an interacting theory and I don't know how to calculate this. But what I can do is I can, as we showed a rigorous way, that's perturbation theory, to describe or calculate this G as a function of a power series in lambda. And if this power series converges, then I can obtain the result, right? So it's lambda to the n, gn, gn. Okay? So I can try and approach it from this point of view. And sometimes this series converges, and then I'm happy. And sometimes it diverges. And naively, I would say 9 people out of, or maybe I should say 999,999 people out of 1,000,000 would probably just give up at this point. But then you have brilliant people who actually say, maybe I can actually read off something from the way this series diverges. Okay, and I can actually resum it, although it's a diverging series. Okay, and read off the analytic structure from this. And that's what they're talking about. That's called resummation. So there are all sorts of families of ways of doing that. Okay, there are many, many ways that people have developed to resum diverging series. And that's the kind of techniques they use. So what you have here is the where is this? What you have here is the lowest order corrections of this expansion. But you can first of all do better. That's one thing, and by going higher loops, basically, and and also you can find, you can. It's always a question of so you assume, basically what we're assuming in this relationship is that this is an analytic function of lambda. And then the question is, how do you analytically continue it? So you can choose different methods. The simplest method, which is what you would naively guess, right, is you can try and write this, as some, for example, you could, the most naive guess would be to guess something like G01 plus lambda G0 or something like that. And then Gn would be some G0 to the n or something like that.
Yes.
So you can try and do, like, that's the most naive thing to do.
Okay.
But you can do more sophisticated structures like that, that's called pade. Like you can take a bunch of these GNs. Like you can, this would be like the simplest thing where you just take G0, but you can take like maybe G1, G2, G3, and then expand it, lambda to the, this can be like a power, so you can have like G1 lambda squared plus G2 lambda cubed, and here you can also have some powers, and all these structures are analytic, so it's nice, and this is called pade. Pade is like the simplest thing, and that's all I know how to do. No, but there are some. There's like Borel resummation, which is more sophisticated, and This is an art, and the people who do it should be praised. It's really a thing. But those people who know how to do it can try and do it. And the beautiful thing is that just like we did here, they just try, and then you can stick in the values and see what you get. They are capable of reaching a situation where they agree with experiment, like exactly. To, I don't know, third digit or something. Which is pretty amazing, I think. Right?
Yes.
So that's the point. Okay, so let's start with fermions. So what we want to do now is we want to take so now we have this new toolbox, and now we want to apply it to fermions. So the RG approach to interacting fermions. So once we apply it to fermions, we immediately see that we have a problem. And the problem is, right, if I draw the dispersion relation, let's assume that these are parabolic fermions. Then I have a Fermi surface, right? And this is like minus kf, this is like kf. And if I draw it in momentum space, I have a Fermi C. And we know that the volume of this inside is related to density via So I didn't teach you this Lattinger's theorem, but Lattinger used so Lattinger and Ward developed this functional, which is a method of describing the corrections due to interaction to the Green's function. And using this functional in a very clever manner, Lattinger was able to show that the area, the volume enclosed by the Fermi surface is, as long as you have such a Fermi surface, is still given by the particle number. So that means that, and we know for non-interacting fermions that that's the case. The beautiful result is that it doesn't matter, like as long as the Fermi surface is left intact, no symmetry breaking or no non-Fermi liquid behavior or something like that, we know that the volume enclosed by this Fermi surface, regardless of interaction, is still going to be related to density. Now, why is that a problem for us? Because we wanted to make a transformation,
Is this the same Lattinger from Tomanaga?
Yes.
Okay. What
she taught us what?
the Lattinger theorem?
No, she taught you the
The Tom-
Lattinger
Tom-
liquid theory in 1D.
Yes.
That's something completely different.
Okay, so that's the same.
Lattinger did many things.
Okay.
It's surprising he never got like a Nobel Prize or something, but he has many important contributions.
Okay.
Okay, this is he's actually extremely non-trivial physicist. He did many mind-blowing contributions and completely different topics.
Okay.
So this one is one of them. But this is completely different. This is okay. So the larger liquid theory is about obtaining the low energy effective theory of interacting one-dimensional systems. And what they were able to show is that you always have these kind of emergent quasi-particles, what we would call quasi-particles, which are just density modes. And so that's larger liquid theory. And you know, there is some beautiful relation between these modes and the fermion operators. So despite the fact that the fermionic operators are not quasi-particles at all, you still have these quasi-particles, density modes, and you can calculate using this. You can calculate many things. That's larger liquid. Okay, and the larger liquid, it can be a fixed point of one-dimensional systems. And if you add perturbations, maybe I'll add that in the exercise. You can add perturbations, and you can see how, like, these perturbations can take you away from this fixed point. So you can use our G actually to study this. It's very, there are many problems you can attack using RG. This Ladinger theory is something completely different, and the statement is that when we studied condensed matter physics, we studied that the area inside a Fermi surface is related to density.
Yes.
Okay, that's for a non-interacting gas.
Right.
What he showed is that this relation is not modified by interactions. That's basically the point. If you want, the gist of the proof is the fact that the chemical potential, right? That if you write imagine that you write some functional of the full Green's function. Imagine that you and this is this Ladinger word. Actually, it's this and the self-energy. So this is the Ladinger word functional, which is like a free energy, if you write. And the statement is that this, with regard to mu, is equal to, or maybe with a minus, is the particle number. But the point is that this mu, it actually appears in the non-interacting Green's function. And that's the essential thing. That's where it showed up. But that's I'm not showing it. But all I'm trying to say is that if we would do a resummation like this, a stretch, if we would do our stretching, right, then we would actually change, right? So we might try to integrate out some high energy states, and then, but then what we would have is that our new, our new theory would have like a larger inflated Fermi surface and a larger density. So we have a problem. It means that if we just apply the RG transformation we just studied to Fermi C, then we would go from one system, one density, to a different density. Okay, so the theory is not invariant under this. So here what we're going to use is what is known as this Shankar RG. So what Shankar proposes, he says, let's actually maybe use this.
Finally, I think I understand after reading that paper 20 times. Why did he do from the beginning the linearization?
So let's imagine that we have our parabolic dispersion like this, and we have a Fermi surface, epsilon Fermi. So what he's saying the excitations of a Fermi liquid, if you have a Fermi liquid at low energy, then all these states here are basically frozen. Okay? So the real excitations are like particle holes around the Fermi surface. So let's define our cutoff around this. What do I mean by that? So imagine that I take these points this. Then I get basically two shells. That. And like that. And in between them, right, I have my Fermi surface. A different cut. So I have this kind of Fermi surface. And then the idea would be that this is what we would call Kf. And then the width of this window is like 2 times lambda. That's our cutoff. So we're creating a cutoff in momentum space, which is the momenta away from the Fermi surface. Now, what we will see shortly, well, probably next week, is that when lambda is of order Kf, then it's a mess. The whole thing is a mess. And there is no kind of universal behavior that we can assign. For example, one of the things that was crucial to us in the previous expansion is that we were able to neglect the momentum dependence of the quartic term. Like under RG, the momentum, even if we start from a momentum independent quartic term, the RG generates momentum dependence. But then, as Joseph explained to us last time, this momentum dependent terms are irrelevant under RG, and we have a general scheme to neglect them. Here, what's going to happen, in fact, is that when we do the RG from here to here, okay, when we start with a cutoff of the order of Kf, we're going to generate these momentum dependence, and there's going to be no rigorous way to neglect them. Okay. Only when we reach the limit where lambda is much, much smaller than Kf, that's the limit where we will have, rigorous momentum independent couplings. Actually, we're going to have, even if we start with a single interaction, we're going to have several of these couplings. And only then we can kind of generally neglect this momentum dependence that we develop and have universal, momentum independent coupling constants where we can solve their, we can discuss their flow. And this is very similar to kind of Fermi liquid theory. I don't know, you probably never studied the rigorous way Fermi liquid theory, but Fermi liquid theory is exactly about renormalizing. So you kind of, it's a phenomenological theory, but you kind of, the philosophy behind it is that we're looking at low energy effective theory, and indeed Landau in his brilliance just guesses this form of the interaction with this momentum dependence, right? If you look at this interaction, you would even identify that it's not even translationally invariant, right? Because a translationally invariant interaction has a constraint on the interaction. So his Fermi liquid theory is based on interaction Hamiltonian that has like k and k prime, and then you have some f of k and k prime, delta n of k, delta n of k prime, where these are fluctuations of density, but with without some q. So delta n k is like c dagger k c k minus the expectation value of c dagger k c k, which is like the density. Okay, so this thing, because it has both k and k prime and is not like the difference between them, it's obvious that it doesn't conserve. It's not translationally invariant.
Right.
And this whole momentum dependence, it comes from this renormalization. The way I like to think about it is that when when you normalize the interaction, then each quasi-particle actually has a cloud around it, and this cloud of quasi-particles can actually depend on the direction of momentum, and then you can kind of have this kind of directional dependence, which doesn't really look naively translationally invariant. So somehow he guessed all this, and all this mess is kind of something we're avoiding. So what we're going to do is we start from this limit. We assume that whatever happens when we go from the really microscopic scale to the scale where we want to do the RG is what it is. I don't know what to say about it. RG can't deal with it. But what I can say is eventually if I go to really low energy scales, then the RG can take over and really give me something informative. And the point is that it's not such a bad situation, because as you know, the Fermi energy, for example, is 10 eV in a metal. So we have a lot of energy scale, for example, and the Kf is proportional to the microscopic interparticle distance. Mm-hmm. So if we want to study response or phenomena on the scale of microns or millimeters, then that's not a problem. We have a lot of orders of magnitude to flow between them. So lambda can still be microscopic. It can be like 10 nanometers, like 1 over 10 nanometers, or 1 over 100 nanometers, and we still have a lot of room to breathe until we really reach the Fermi surface. Okay, maybe 100 nanometers is a bit big, but something like that. Okay, so that's the philosophy of what we're going to do.
This cutoff is like here for practical reason, like it's like omega de Bai, or it's different from omega de Bai in the spirit.
No, it has nothing to do with omega de Bai.
I mean, we put omega de Bai just right for practical cutoff.
Why do we put omega de Bai? Where did you bring this omega de Bai?
No, just ליגשר, פשוט cutoff. We used omega de Bai.
When did we use omega de Bai?
In statistical mechanics, that's the matter. General in physics, we use omega de Bai, right? It's just a cutoff.
Oh, I know what you're talking about. You're talking about when you compute the specific heat of a crystal.
Yes, for example.
The phonon contribution.
Yes.
No. That's something completely different. That comes for a different reason.
Okay.
That has nothing to do with this business. Because there what you have, okay. What you do is you assume that omega of k is some velocity times k.
Yes.
Now this is of course, this is some linear expansion. Now you know that the actual dispersion, omega of k versus k, kind of looks like this.
Mm-hmm. So it's
as you've derived in our
yes.
Now what you're doing is you're assuming, right? So you can do two things. You can either take this initial velocity and continue it all the way to the zone boundary, or you could try to make a linear dispersion. But overall, the scale is of order, the bandwidth, maybe twice the bandwidth, but not more than that. So that's why we set a cutoff. Okay. And here we're doing a cutoff for a different reason. Okay. We're doing a cutoff because you can, let's imagine that you're God. Like you can do the RG at any scale. You can sum up all diagrams.
Okay.
That's fine. That's what happens. Tzvi can reassure us that he's going to complain that I am making God
personal.
I'm humanizing him, which is of course why? How can I even dare think of God wanting to do RG? This looks like some pathetic attempt of human beings to understand something way more complicated that he doesn't even need to understand because he invented it. But the point is that let's imagine I could do all this RG to all scales with everything.
Okay.
Then the philosophy would be that when I do it here, it's just completely messy and develops a lot of terms. But eventually, when I approach the low energy behavior, suddenly some universal structure emerges. And that's what RG really is about. It's about universality. I want to be able, so I didn't mention this, I think I mentioned it last time, but one of the achievements of this result by Wilson and Fisher, especially when we extend it to 3 dimensions, is that even when the mean field theory breaks down, universality still exists. And what does universality mean? Universality means that, you see, even if I start here, or here, or here, I'm always controlled by the same fixed point. I see the same behavior, and it can be many different microscopic starting points. It can be a spin system, and we saw like liquid gas, and it can be like cold atoms, and it can be, I don't know, germs that have like 2 configurations or something. It can be many, many, many different systems, all having the same universal property. And that's what we're looking for here. We want the universality. So the philosophy would be, okay, I have a problem because I don't know what the starting point is. But what if I don't care what the starting point is? What if I could tell you the answer for any starting point, and you choose the starting point? I don't know what it is. I'm just going to show you what happens generally. Okay. And that's kind of the philosophy.
It's like the Green's function, right? That they solve a family of problems.
Yeah. Okay. Yeah. That's In general, that's what we always want to do, and that's like my son. I remember that when he was like I don't know, like 3 years ago, they started doing variables, and he's like, "What is this story about variables? What is x? Why do I need this x?" And so that's what you explain. You explain, when you solve problem by problem. Same story, yeah. So let me just write the theory, and then next time we can discuss it. So, let's write this universal, presumably universal theory that we wanna.
And this freedom only emerges above 1 dimension, right?
What?
This freedom only emerges above 1 dimension.
Freedom. What's the freedom?
Like this circle.
Well, in 1D there is no circle.
It's there are 2 points.
But 1D, the problem with 1D is that it's actually very interesting because the Fermi surface basically makes the problem effectively 1D. But the higher dimensionality gives a phase space argument that stabilizes this approach. In 1D, you don't have enough phase space constraints, and it actually breaks down, and Fermi liquid is not a stable fixed one.
Okay.
Yeah, I don't know if I'm probably not going to have time to show that, but so we're going to start immediately in 2D. So then we have an integral d omega over 2 pi. This is like S0. Integral from minus lambda to lambda. An integral dk, let's call it dk, from 0 to 2 pi d theta times say kf or something. And maybe we have spin also, so we're going to have psi bar spin omega k theta, and then we have I omega minus VFK psi sigma of omega k and theta, and our interaction term is going to be equal to 1 over 2 factorial squared, which is just choice, times an integral k omega theta p psi bar of 4, psi bar of 3, psi of 2, psi of 1 u 4, 3, 2, 1. And then this integral here, p omega theta, is actually pi j equal to 1 to 3, an integral from 0 to 2 pi d theta j, an integral from minus lambda to lambda d kj, an integral d omega from minus infinity to infinity, d omega over 2 pi j. And then we have something very weird, a theta function of lambda minus k4. And then we have, okay, and so this is what we call the measure. This is this integral. And then the second thing is that psi j, for example, is psi of kj theta j omega j. That's what we mean. And next time we're going to see, so the fact that there are 3 integrals here of every sort tells you that I basically is taken 4 to obey momentum and energy conservation. I did the delta function integral. But then you could ask, wait a second, what is this thing? Like, why on earth do you have this theta function? And what this theta function is just a cutoff coming from the fact that we want to demand all 4 momenta to lie inside this thing. Now the point is that you can, and I'll show you this graphically next time, even when 3, 2, and 1, lie within this shell, it doesn't mean that 4 has to lie in that shell. And we'll see how, because this k here, notice that this k is not a vector. It's not a vector. It's in the same direction of, the momentum. So we have something like, you can think about it that we have something like pj, that's the momentum, is like kf plus kj as a magnitude times some direction n of theta j, which is like the direction. Okay, that's kind of the point. And we'll see next time how to work on this. But yeah. Question, what?
This is written in 2D, right?
2D.
Okay.
Yeah. We're not going to do more than 2D. But actually 2D and 3D, they're not that different, except for some.
Yeah. And the KF comes from the Jacobian, and you just approximate it on the premises, right? You have d theta KF, so.
Yeah.
Right. Okay.
Yes.
Just to make sure.
Shouldn't the green function in the middle be should it be inverse? I omega minus v.
You mean 1 over?
Yes.
No, but this is the inverse Green's function, right? The correlation is 1 over.
Yes, the equation.
This is what we call G0 to the minus 1. The way to see it is to couple psi to a field and then complete the square, right? You remember that trick?
Okay, yes, I know.
So that's Shabbat Shalom.
Yeah, I have another question.
What's the other question?
אפשר אבל בעברית ואז יהיה שבת שלום.
כן. סיימנו, we're done. נירית, you can cut. כן, מה השאלה?
הפי של ג'יי, כאילו מה זה אומר פי של נגזרת של... נכון, יש לך פי של ג'יי של פי KY נגזרת של מה?
על מה אתה מדבר?
למטה צד ימין.
זה?
כן.
זה פסי.
כן,
פסאי.
זה פסאי של J שווה פסאי של K.
לא, זה בסך הכל
כתיב עצלני.
כן, בדיוק, אני כאילו קיפלתי גם את KJ, גם את
זה תטא J.
כן.
אוקיי.
זה נגזרת, פשוט זה נגזרת.
כן, יש לי גם מספר קצת, אז אפשר להשאיר את המספר.
המבחן זה אז באופן רשמי שזה עדיין באוויר.
זה אז באופן
רשמי?
נראה לי הכנס הם איכשהו ה-IPS, אתה יודע, היו המון כנסים שביטלו, שהשתפנו וביטלו.
הם שפרו מייל שהם לא
ויצמן גם.
כן, אבל הם החזיקו מעמד. הם החזיקו חזק וניצחו.
טוב, זה IPS.
למרות שהאיראנים פרסמו תמונה של הטכניון שהם מכוונים אליו.
זה בטכניון.
איפה יהיה, כאילו, איפה שהיה שנה שעבר, בלונה פארק?
באיזה?
לא,
בטכניון.
בטכניון.
אבל לפעמים, כאילו, אוניברסיטות, זה של האוניברסיטה.
והם עושים במקום אחר באמת?
כן.
נראה לי בטכניון.
יונתן, שואל על טנטגרם היום?
אתה אוהב טנטגרם.
טנטגרם זה בשיעורי בית.
צא לקמפינג ותפתור.
בסדר. כן. טוב, אני מניח שאני מתחשב. אז אוקיי, מה ההגדרה של אפסילון? זה טנט יחיד.
קודם כל זה סיגמה.
סיגמה, נכון. אני באמת שכחתי את היוונית שלי.
זה אחד. אתם יודעים שכתבתי פוסט בטוויטר על אותיות יווניות ואינסטלציה?
אוקיי.